So I'm going to talk about the stable set problem on degree D graphs. And this is work with Nikhil Bansal and my student Guru Ganesh. And it appeared in the Stock 15 conference. And OK, so right off the bat, G is unweighted undirected graph. And you know what a stable set is. An independent set, so it's a set that induces no edge in the graph. And for there'll be n vertices. The number of edges is not important out here. Let's say the max degree of the will be D. Okay, and I'm interested in approximation algorithms for this. So I want an approximation algorithm. So I want that my algorithm's independent set size is at least opt times some factor alpha. Maybe I shouldn't use alpha, some factor rho, and this will be my approximation factor. Okay. So right off the bat, we know that any degree D graph has independent set size. Independent set size is at least n over D plus 1, right? And clearly, opt is at most n. So this algorithm, I mean, in fact, the greedy algorithm will find you such a thing, is a D plus 1 approximation. So good. So let me make a thing out here. So a D plus 1 approximation, this is just greedy, and this is trivial. Okay. And the question is, can we do much better than this? And so this question's been studied over the years, and there's a bunch of results, and I'm not going to survey all of them. We only have so much time before T. So let me tell you what was known until 2 years back. So until 2 years back, the following was known. And this scale is some weirdo scale. 0 is somewhere way the hell out there. So it was known that there's an algorithm which is a D over log D times log D approximation. Okay? And in this talk, I'm going to make a conscious decision not to write log terms. So I'm going to just use the Chandra notation and say it's this. So I'm ignoring log factors. There'll be a couple of times when I'll have to write a log, but you'll forgive me for that. There's a lower bound of D over log square D, and this is assuming the unique games conjecture. So assuming the unique games conjecture, we won't do anything better than this. If you're a purist and you like P is not equal to NP, so under that there is a D over log to the 4th D. So this is what's known. So there are lower bounds. Unless P equals NP, we can't do this much. I'm willing to believe the unique games conjecture for the moment. At least, this would say if we can beat this bound, then we are doing something somewhat non-trivial. So I'm looking for this as my goal. Marek.
You're talking about asymptotic.
Absolutely.
D equals 3 or 4.
Absolutely.
Or 5.
Right.
Very interesting.
No, so we're not looking at that. Yeah, absolutely.
So you have this constant.
Absolutely. So our methods, you should think of D as a large constant or a function which is very slowly growing with n. But really,
You're not getting things.
For D equals 3, 4, yeah.
5.
Yeah, no. Think of D as 1,000, million, something like that. Absolutely. Okay. So this is the results that were known. This is due to Halperin. Okay. So earlier this year, Nikhil Bansal gave an algorithm which uses some Shirali-Adams plus SDP hierarchies, and which showed that there was a SDP whose value was equal to, would give you a this factor approximation to the independent set size. And maybe, so this is Nikhil Bansal. So he showed that the value of this SDP, if you didn't really care about finding the independent set, but just the value was the right value, then it was within this factor. So it pretty much closed the answer up to log factors. Okay. But what we were interested in was the question of, so this was SDP, this is the SA plus SDP. So, if you are interested, ask me later on, I'll tell you what it is. What we were interested in was how well does a certain other SDP, a well-known SDP, the theta function SDP, how well does it approximate the independent set value? And that's what the talk is going to be about. So the theorem of this talk, and this is the main theorem, is that a certain SDP called the theta function, many of you know what the theta function is, probably better than I do, is within an order d over log to the 3/2 d of opt. Okay. So this is our main theorem.
Wait, when you use mu plus, it's always log, it's not
absolutely. Yeah, no, absolutely. It's log. Polylog, yeah, log squared would be.
Oh, you're also.
So out here,
Might have been a log.
so it's actually log to the 3/2. It's actually the same thing. So this is what I'm ignoring out here. So it's polylog terms. So this is the main theorem that I'm going to prove. Okay? You good? Yeah. So let me tell you how I'm going to prove this. And essentially, how am I going to, and what is opt? Opt is really alpha G, right? Okay. So I'll give you the general idea of how we're going to prove this. And for that, I'll draw another line. And this line has got nothing, it's kind of related to that, but let's not talk about that. So let's look at how would any algorithm prove to you that the independent set is a certain value, or is approximately a certain value. So let's look at so I want to show that the theta function value over alpha of G. So let's actually look at, let's actually look at this quantity. How much does the theta function say? Whatever this theta function is. It's just some approximation to the independent set size. What does it say divided by n? It could say it's 1, and it could say the value is very small. Okay. Now, here's what I'm going to say. That suppose the theta function says that the independent set size is n over k. Okay. In any graph, greedy can find an independent set of size at least n over d plus 1. I'm going to ignore the plus 1 terms. So on any graph, greedy can find an independent set of this size, right? So what is the approximation factor of greedy? D over k approximate. Right? So suppose I wanted to approximate. So as long as this k is large enough, k is like, so for instance, if k were like log d squared, so then this should be a d over log d squared approximation. Okay? So if the theta function says that I'm small, then even a dumb approximation, even a dumb algorithm is a good approximation. So I would need to do something if the theta function says my value is large. This is where I need to be smart about it. In this case, the SDP says you have a large independent set. I need to pull out a large independent set somehow. Okay? Good. So what am I going to do out here? And this is, I'll give you the high level picture. This is, if you remember this is the main, takeaway message. There's some details. Okay. So what do we know about the theta function? So one of the facts we know about the theta function, which is very nice, is that on any graph, I haven't told you what the theta function is, but on any graph, the theta function is at least the independent set number, and is at most the clique cover number of the graph. Right? So this is whatever the sandwich lemma. Okay? And I'm going to give you loosely why the theta function being large should say something meaningful out here. And I'm going to wave my hands and I'm going to be false, but I'm going to make this true. Okay. Theta function is large. This means that the clique cover number is large. I need a large number of cliques to cover my vertices. Right? So morally, and this implication is within quotes, this is not really if this is large, this morally means I have small cliques in my graph. It's not really true, but squint a little bit. Now, if my graph has small cliques, what do I know? What does Ramsey theory tell us? If a graph has small cliques, it has large independent sets. Large stable sets by Ramsey theory. And if I have large stable sets, then I should get a good approximation out there. So that's the moral of the story. So I'm somehow saying that, if the theta function is small, then greedy is good. If the theta function is large, then by Ramsey theory, I should pull out a large independent set. Okay? So let's make this precise. We good so far? We happy with whatever we've seen? Okay. Let me see what I can erase. Oh, that's that. Sheet out here. Okay. So I'm going to use Anders. You have a question? Okay. Perfect. You feel free to ask questions whenever. Think, and let me know. Ask me anytime. Okay. Okay. So in order to give you a good approximation, so far we have agreed that as soon as the theta function tells us that the value is small, I'm done. I have a pretty good approximation. The theta function tells you the value is large, I need something smart. Okay? And there's one fact. So there's two facts that I'll use about the theta function. Oh, you know what? I keep talking about the theta function. Let me just write down the theta function out here. So theta of G is a SDP, which is minimizing the following. So I write the theta function as a vertex program.
This is normally written as less than or equal to the fractional stable set. I mean, is there another thing that goes in between? So when theta is normally, I think of it as a body that's sitting between the stable set polytope and the LP relaxation of the stable set polytope.
Yes.
And that would go in between the chi bar? Yeah.
I think so, yep.
That would go between chi bar.
So out here, right?
Right, yeah. But that is not of
It's not for right now. It's good. Okay. So you were thinking of the Q stab. Yeah, so that would go somewhere in the middle, right?
Rational stability.
You're writing just numbers.
Yeah,
alpha star. Okay. But I don't think we'll need that. I mean, yeah. Good. So theta, good, is minimizing what? So I'll write this as a vector program. And I'll say that we have vectors for every vertex I of the graph. And we have one vector. So we have a vector which I'll call V0. And then I have vectors V1, V2, up to Vn. And I have the property that Vi dot Vi is equal to Vi dot V0. I also have the property that Vi dot Vj is equal to 0 for all ij being an edge of the graph. So I'm assigning vectors to vertices so that if there's an edge, then these are orthogonal to each other. The projection onto the V0 is the same as the squared length of Vi. And I'll get, what else do I want? I want minimize, clearly I should maximize sum over I, Vi dot V0. Okay? We agree that, those of you who've seen the theta function, this is one of the definitions of the theta function. Okay? So really what we are doing is we have this sphere around V0, and all these guys are really kind of so they're all, and if there's an edge between V2 and this guy, then they're orthogonal to each other. Okay? Andras.
When I was still not here, you wrote opt alpha of G. That's just alpha of G, or?
That is just alpha of G. Absolutely.
We're not controlled.
That was good. Okay? So this is the theta function. There are two properties of the theta function, one of which we have already written down out here that we'll need. And the other property of the theta function is that, so let me call this quantity, Vi dot Vi, which is Vi dot V0, which is the contribution to the objective function. I'll define this to be Xi. It's like the contribution of I to the objective function. Okay? And here is a fact. It's easy to prove. X on a clique, which is, again, I can define this to be sum over I in the clique Xi, is at most 1. So the beauty of this thing is that the amount this gives to any clique is at most 1. Right? Good. And this kind of just follows from these orthogonality constraints and this constraint. It's kind of like you have the unit vector out here, and you have all the guys in the clique, they have edges between them, so they're all orthogonal to each other. And you have this unit vector and its projection, each of these guys has projection equal to the squared length. Now it's like Pythagoras' theorem. Their sum of their squared lengths can't be more than 1. And you can prove this. Okay? Good. So these are now we have all the ingredients, and now I can, well, all except one. There'll be a Ramsay-theoretic theorem that I'll need, and I'll state. Okay. Maybe 2. Okay. So let's go back here. Go ahead.
There is lots of hint about the Ramsey number, which is quite similar to D over log D.
I'll come to that, or at least I'll come to a variant. Yeah. So I'll mention a bunch of results, and then you tell me which one of Kim's you're thinking about. Okay. Good. So here is one more fact I'll throw at you. I'm sorry I have to throw in this fact. If your value of theta is greater than, and this is the time when I write down another log d over log d, and let's put down an 8. just to be very precise. If the theta function value is pretty large, then in this range, Halperin gave a SDP rounding. Those of you who are familiar with the work of Kargar, Motwani, and Sudan style algorithms, there's some SDP rounding, which gives you a pretty good approximation. And how good an approximation? Let me get a color out here. It'll give me a d over log square d approximation in this range. Okay? So in the high range, I have this algorithm, some black box, don't need to worry about it, which will give me a d over log square d approximation. In the low range, I have greedy, the dumbest algorithm in the book, which will give me another d over log square d approximation. So I need to worry about this range. Okay? Good. So let's just imagine that we have a solution where every vertex lies in this range. That is, every vertex I has xi, which lies in this range. So I gave you a graph, solve the theta function SDP. There are a bunch of vertices. Imagine that each of them has xi, which lies in approximately between 1 over log square and 1 over log. Okay? So what does the graph look like? So if each xi lies in 1 over log square d, to let's say 1 over log d, doesn't really matter. What is the max clique size in this graph? Right? This graph can't have too large a clique. What is the SDP value? The SDP value is at most n over log d. Each vertex can give me 1 over log d. Right? So the thing is, if only I could claim that there exists, that the independent set size is at least n over d log d. If I could claim that the independent set size was this much, then this divided by alpha would be d over log square d. That'd be great, right? I'd get a d over log square approximation. Okay? So I need to claim that on a graph with max clique size this much, there exist independent sets of size this much. So I need a Ramsay-theoretic result. Now I've made everything formal, and I'm asking for the following kind of question. Let G be a degree D n vertex graph with no cliques of size R. What is alpha G? Okay? And ideally, I want to say when R equals log square D, I want to get such a result. Okay? Now this, those of you who know this stuff will realize this is a well-studied problem. So let me tell you a bunch of results. So prior work. Maybe I'll just write it out here. So beautiful theorem of Aytai, Komlosh, and Samaredi says that if you have a triangle-free graph. Oh, by the way, degree D n vertex graph, you know that independent sets of size n over D, right? That's one of the first things we said. So in triangle-free graphs, you get a slight boost. And how much boost? You get a log D boost. I'm cheating all over the place, and the constants are going out of the window, by the way. So they had a tiny constant out here. It was improved later. You don't want to know. Anyways, this is a beautiful paper. It introduced essentially the idea of the Rodel nibble, which then Rodel later on used to prove a bunch of other things. This is a very nice paper. Okay. This is triangle free. I wanted KR free. So then there's this paper of Shearer, who said, well, if you have KR free, what you get is n over D log D over, and you're going to pay something which depends on R. Now what he showed was that you get an R loss out here, and you get a log D loss out here. This is Shearer's result. So you have independent sets of size at least this much. And I might as well write down the question that I would like to prove. And I'd be very happy if you guys can prove it for me. Open question. Show that alpha of G is at least n over D log D over log R. So I want the dependence on R not to be linear but to be logarithmic. And this log term should really go away. I can show you the proof. You'll see why it comes. Removing this log term has been a long-standing problem. This was in the 80s, so it's been 30 years. We still don't know how to remove the log term. Okay. What do we prove? We prove alpha G is at least n over D log D over log R. And this would be great. We don't know how to prove this, so we prove this. Okay? And if you plug in R equals log square, then this is like this logs terms that we were removing. And we are left with n over D square root log D, which gives this log to the 3/2. And if you could do this, then it would give log square D over log square D, which would be the optimal result. So this is what this is really an open, I want to present an open problem. I'm giving an hour, 45-minute long talk. But this is the problem I would like you to help me with. This is what I can prove. Alanta. Okay, so Nikhil Bansal had showed that some SDP using several rounds of the hierarchy gives you something. I want to show that the Lovasz Theta function is as good as anything else. Exactly. So this would imply that the theta function of G is D over log square D approx to alpha. And what this implies is that theta function is D over log to the 3/2 D And the 3/2 is just coming from this stupid square root. Okay? So that's kind of the bottom line. What I can do now, actually I should figure out how we are doing on time. It's good. Oh, perfect. Good.
And this is not with a missing log-log factor.
This one? You're right. This is with the missing log-log factors. This has an unfortunate, another log-log which is sitting out there. So there are log-logs, unfortunately. And we lose log-logs for similar reasons as Cheryl lose log-logs. Okay. So what I can do is in the next 15 minutes or so, I can give you an idea of this proof. Actually, maybe before that, before diving into the proof, let me tell you one more set of results, which are very interesting, and there's some really good open problems out here. Okay. So G is a degree D and vertex graph with no KR. This is asking what is the independence number. I can ask the same question, same G. Give me bounds on the coloring number. Okay? Degree D and vertex graph, no KR. Give me bounds on the coloring number. And this is related to this work of Jong-Han Kim, who showed that the graph has no C5, no cycle of size 5. Then you get some bounds. So out here, there are two amazing results by this guy called Johansson, Anders Johansson, who showed, his first result showed that if the graph is K3 free, then chi of G is at most D over log D. D is trivial, right? D plus 1, whatever. Just the easy part of Brooks's theorem. So Johansson showed that you can get the same log D boost that Aythay-Komloshan Semeradi get if your graph is triangle free. Okay. And then Johansson, so this was 95, unpublished manuscript. The place where we found this was this book of Molloy and Reed. Who explained this thing, beautiful explanation, beautiful algorithm. And then Johansson in 96, in an even more unpublished manuscript, it's not even in Molloy and Reed, showed that if you have a KR-free graph, then chi of G is at most, any guesses? I wish it was that, R times log. So it's exactly the analog of Scherer's result. So whatever Scherer gets, Johansson gets the same thing. And both these things use the so-called Rodel-Nibble method. So if probabilistic combinatorics appeals to you, this is beautiful stuff. And I'll mention an open question out here. What's that?
I want to know where Bruce Reed was. He's in Barcelona.
So the open question is, can you get the chromatic number of G to be at most D square root log R over log D? So can you get a chromatic number result which matches our independent set result? And I don't know how to do this. If you can do this, and if you can do this algorithmically, by the way, both these things are algorithmic results. They run in near linear time, use the Lovasz local lemma, and give you colorings of this performance. So if you can get this algorithmically, this will imply clearly something about an algorithmic version of our result. All our result says is the value of the theta function is good. It doesn't say how to find an independent set. If you can do this algorithmically, you'll get an algorithm to find such an independent set. Open question. Okay? Good. So that's kind of the, so this was the Ramsey theory board. I'll maybe move it up.
Oh, this is being going down. I'm wondering if you can get the number. Why can't you just delete a node and
Exactly. And also, sort of, it's, if you delete the node, yeah. If it doesn't go down, then you, so are we talking about the independence number, right? So then you could, I guess, throw it away. But if it, but suppose it goes down by a little bit, then what should you do? So then I have no control over how to. If it were exact, then I could know exactly when to do it. But in these approximate cases, I don't quite know what to do. So yeah, the self-reducibility kind of breaks down. Any questions about all this so far? We good? Okay. So maybe what I'll do, and I don't have too much time. What I'll do is, I have time until you guys leave for cake. But here's what I'll do. I'll show you the proof that I love the most. And it's not my proof. It's got nothing to do with my proof. I'll give you Scherer's proof of this fact. You can read it in the Alon Spencer book, but I'll save you that reading. But if you don't understand what I say, you can read it again in the Alon Spencer book. And along the way, I'll be able to indicate why we get the results we get. But
comparing your bounds about T and alpha, can you get interesting results about the T alpha again?
The key bar alpha again. Not that I mean, no, not that I know of, Andreas.
So when you have a good bound for theta in terms of alpha,
right?
Still notice so there's the right hand side.
Uh-huh.
Can the gap between key and alpha be big when the gap between zeta and alpha is small? So you get in terms of d good bounds for theta over alpha.
We get good bounds for theta over alpha.
In terms of d.
Right.
And
I don't quite know how.
D between key bar and alpha, it can't be bounded.
Not that I know of. Don't see it. I'll have to think about it. Yeah, okay. So let me show you Scherer's proof. Good. Good. Okay. So this is Scherer's proof. Okay. So what do we want? G is a graph, degree D, and vertex K3 free. I want to show that alpha of G is at least n over D log D. So step 1 of the proof, pick a random independent set. So proof. And the proof will be an example of what is known as the entropy method by now. Proof, let S be a random, uniformly random, stable set. Okay, could be empty, could be the maximum independent set, could be anywhere in between. This is a completely random stable set. And I'll claim, so want to show that the expected size of S is at least n over d log d. Okay, so clearly this shows that alpha is at least that big. Good. Now, instead of counting the size of S, let's count the expected number of edges in S cross V minus S. Okay. Okay. Let me make my life easy. Let me say it's D regular. Nothing really changes. The proof will go through for maximum degree D. It's just making my life easy. So if they were, if what is the number of, because S is an independent set, every vertex in S will contribute D neighbors in this collection, right? So it's equivalent to show that this is at least n log D. Okay? Instead of counting the size of S, I'm counting the number of edges going out of S. So it's equivalent to show that the expected number of what I'll call in-out edges in the neighborhood of a vertex V is at least log D for every vertex V. For every V, the number of in-out neighbors, in-out edges in its neighborhood. So V is out here. Maybe I'll draw it out there. V is out here. It has degree D. I picked a random independent set. I'm looking at how many edges out here have one endpoint inside S, the other one not in S. Okay? And I want to show that's at least log D. Okay. Good. So I just need to show that last statement. Let me do it. So there is V. This is the neighborhood of V. And this is the rest of the graph. Okay? So let me pick, I've picked a random independent set, but let me pick it in two stages in some sense. Let me pick the part of the independent set that lies out here. Okay? And I'm going to extend it to an independent set in this part. Now, if I picked these guys, say I picked this vertex out here. It had an edge to some vertex out here. I can't pick this guy, right? Won't be an independent set anymore. So look at all the vertices out here which have neighbors in here. Clearly, I can't pick those. So to pick a random independent set, I first pick the independent set conditioned on this part. This kills all these vertices. Now I should pick a random independent set from the remaining. We happy with that? Good. So let me call this part X. It's a terrible notation, but I'm just following Cheryl's in my mind. I don't want to change notation at the last minute. I'll get confused. So there is X. X is the part that I'm going to pick independent. It's still up for picking. And there is this vertex B. So how are we going to pick an independent set? There's one independent set which picks V. And then once I pick V, I can't pick anymore. So there's one independent set which pick V. Suppose I don't pick V. What are the independent sets in V union X? It's an independent set of X. What are the independent sets of X? What property did I know about my graph? Degree D, n vertex, triangle free. All these are neighbors of V, so there can't be any edge in here. So this is all, the whole thing out here is an independent set. So I can pick any subset out here. So there are plus 2 to the little x. Let little x, little x be the size of capital X. So there are 2 to the little x independent sets out here. Okay? And there's one independent set which is just this one. Okay? So let's go back here. So the expected number of in-out edges is equal to, I'm going to pick a random independent set. So one of those 2 to the x plus 1 random independent sets has D in-out neighbors, because if I picked V, all D of the edges are in-out edges. Plus, with the remaining probability, it will be the expected number of in vertices in X, right? Because otherwise, if I didn't pick V, how am I going to get an in-out edge? I better pick this endpoint. Fair enough? Oh, so an in edge is an edge where one endpoint is in the independent set and the other one is out of the independent. We good so far? That calculation is trivial, right? Okay. Now this is either x is less than half log d, let's say. In which case, this is like 1 over square root d. D over square root d is clearly greater than log d, asymptotically. Mark, this is one place where we are using asymptotics, for large d. Otherwise, x is, then the right-hand side is at least the first term, d over square root d, which is at least log d. Or x is greater than half log d. Then ignore the first term. This over that is basically 1. So it's just this, right? Now what is the expected number of vertices in X? The expected number of in vertices in X is at least the size of X over 2. Right? So this is therefore RHS is at least the size of X over 2, which is little x over 2, but little x was at least this much. So this is 1/4 log d. I mean, this is just some stupid thing, right? Once you have this expression, you know how to minimize this. And if you minimize this, you'll get log d on the right-hand side. And that's pretty much it. So the proof said, pick a random independent set, count the number of edges going between the independent set and the complement. And how do you do this? You just look at a vertex and show that the number of edges in its neighborhood are going to be large. A simple probabilistic argument. The important thing out here, maybe I'll mention, is that we used somehow some control over the sizes of the independent sets in X. Because we said, well, look at the number of this is just the number the size of S intersect X. The expected size of a random independent set in X. This is what we used. Now in general, you can try to control this using the Ramsey bounds, which say that this part is R minus 1, KR minus 1 free. So the Ramsey bound will give you something. So for instance, you could say that in general, if you have a KR free graph, this part has no cliques of size R minus 1. So we know by Ramsey's theorem that there must be an independent set of size at least X to the 1 over R minus 1 out here. And this will give you Scherer's bound if you work at it a little bit. But maybe I shouldn't. It's late enough in the day. I should kind of stop here. But this is Scherer's proof, right? This says no matter, in either of these cases, the right-hand side is at least log D, which is what we wanted to prove, So the proof is very simple. It's not algorithmic. In fact, the first step is not algorithmic. Apart from that, everything is very simple. If you could make this algorithmic, also an open question, which several people have asked, we don't know how to prove it. We have to go through Johansson's machinery. Johansson's machinery is a lot of machinery. This is such a simple, beautiful proof. So algorithmically, you can match the n over d log d using Johansson's result up there, but that's a lot of machinery. It's there's so much Lovasz local lemmaing going on that that's another beautiful proof. But this is a book proof somehow. And I feel like there should be a book algorithm to go with the book proof. I don't know. That's what I hope. But also, a different algorithm for this problem we don't know. So, at least in the KR free case. Triangle free is easy. You can do other things. But so that's pretty much where I'll stop. What I didn't show you are the various other Ramsay-theoretic results, but if you're interested, come and talk to me. I'm here for the rest of the week. I can tell you about these things. Maybe we can nail that problem out there. I had a weighted version of this as well. So, which I actually don't know whether it's, okay. So if I gave you, it's true. So I'll give you a weighted graph now. Node weighted. So now I want you to give me an independent set, alpha of G, or give me an independent set S such that the weight of S is at least the weight of the vertex set over D times log D. This is possible because I'll use Johansson's result, color the graph using D over log D colors, and pick the heaviest weight class. Can you give me a direct proof using this approach? A different proof. It's only because I'm interested in this approach. I don't know how to show it. Anyways, I'll stop here. Thanks so much.